Hi and welcome back to another lesson in the physics video series. Today we will be discussing the force components on an inclined plane. Up to now, our surface has been flat and any object that has been accelerated on that surface has accelerated axially, meaning along the x-axis. However, in this new variation, we're going to incline the surface a certain number of degrees theta, and we're going to see how the force components change based on the angle. Okay, let's get started. The first question we need to answer is, what is an inclined plane? Well, an inclined plane, as you see here, is this triangular wedge that has a block sitting on it. This block may slide down to the bottom of the plane, and the only force that's acting on the block to cause acceleration is the weight of the block. But the problem is that this object, while it wants to fall straight down, is interfered with by this ramp, so it can only fall down the ramp or slide down the ramp. And when it slides down the ramp, we ask ourselves, what part of gravity is actually pulling the block down the ramp? Obviously, it is not the full effect of gravity, because if it was, it would be going straight down along the y-axis. But it's neither moving along the x-axis or the y-axis, so it has to be a part of gravity. And this block, when released, will slide down the incline towards the bottom. As it does that, it may or may not accelerate, depending on the component of the weight and the frictional balance. Let's begin by explaining each one of these vectors. Ironically, while it may seem like there are many vectors on this page, there is actually only one action vector, one force of action, which is the weight of the object. All the other ones are reaction forces of sorts, except for the component of the weight. Let's explain what we mean by components. As you recall from the last lesson, any vector that's on an angle can be assumed to be the hypotenuse of a right triangle with its two legs, one of them on x and one of them on y, acting as components of the original vector. Here we have a familiar diagram. Any vector on an angle can be considered to be the hypotenuse of a right triangle. The legs of the right triangle are perpendicular components to each other. We would ask which quadrant is each one of these vectors in, and that would determine which way the legs of this right triangle point. Well, this works very well when the x and y axis are positioned as they are. In this particular way, x is the traditional horizontal and y is the traditional vertical. But unfortunately, in the inclined plane, we don't have the same orientation. It seems that there is nothing on x and y. Well, technically, the weight vector, which points down, is on the true y-axis. But there's a simple solution to this problem. All you have to do is tilt your head a little bit to the left, and you realize that this surface of the inclined plane is really the new x-axis, and this normal and perpendicular line really are the new y-axis. So basically, when you look at this weight vector down here, it turns out to be a quadrant 3 vector after all, and it's very easy to resolve it into its two components. Let's explain that in detail. This weight vector makes an angle theta to this perpendicular line as this incline makes an angle to the horizontal. This can be proved geometrically and will not be covered here. However, the angle that's here in the bottom corner of the incline is the same angle that the weight vector makes with the normal line that runs through the surface. Now, when we tilt our head a little bit and realize that this is actually just a quadrant 3 vector, we see that in relationship to the surface, this black vector is resolved into two components. The perpendicular component, which is blue, and the parallel component, which is green. Now, we're not using x and y anymore, but we're using two symbols. Parallel, which looks like a little number 11, and perpendicular, which looks like an upside down T. The parallel component of the weight vector is the part of the vector, which is green, that is literally parallel to the surface of the ramp, or the new x-axis. So technically, F parallel is really the new x. We won't be using x's and y's in this type of problem for clarity. The new y-axis is really this perpendicular component, but there is a difference, and this is very important. This parallel vector is opposite of this angle, and opposite always goes with sine. So F parallel, which is the accelerating force, that is the force that pulls the object down the ramp, is based on the sine of the object. So this would be mg times the sine of this angle. The blue vector is the perpendicular component. Perpendicular to what? To the surface that's holding up the object. So the surface holds the object up and gravity wants to pull it through or down. So the new up is the orange direction. The new down is the blue direction. The perpendicular component is the part of the weight which would like to fall straight downward or through the surface. But of course, the surface does not permit the block to pass through it, and so it resists it or pushes it against it, and that push is along the same 90 degrees to the surface, called the normal force. The table's normal force holds the object up against falling straight downward. So just like in the last problem, when there was no tilt to the surface, the normal force, which happened to be equal to the weight, in this case the normal force is equal to the component of the weight on that same dimension or same axis. So the normal force and the perpendicular component of the weight are equal and opposite. Just like before, when we realized that F parallel was opposite of the angle, we now see that F perpendicular, the blue vector, is adjacent to the angle, and adjacent goes with cosine. So the full force vector, mg, times the cosine of the angle equals perpendicular component. So in summary, we can see that F parallel is mg sine theta because it's opposite of the angle, and the perpendicular component is mg cosine theta because it is adjacent to the angle. The parallel component gets translated and brought to the center of mass right here. So this F parallel and this F parallel are identical vectors. They're not doubled. It is just the same vector translated and moved up. So you can see that the F parallel pulls the box down the ramp. This is the accelerating force, the force that pulls the object down the ramp. Now, if there is any friction, the friction will be 180 degrees opposite to the parallel force. And here is the friction. F equals mu normal. So this is the normal force right here. So the friction will be the Greek letter mu, coefficient, times whatever value that the mg cosine theta gave us. These two pairs of forces work together to, 1, pull the object down the ramp, and 2, hold the object up and not let it pass through the ramp like if it was thin ice. Let's now take a look at the force components on the inclined plane for 5 varied angles. We'll start with the one you know, which is theta equals 0 degrees. This is the flat incline. There's really no such thing as a flat incline, but when the angle is 0, that's what this would be. The weight would equal the normal. Exactly. There is no left or right force. There is no F parallel component because the sine is 0 and the sine of 0 is 0. And as we go to a shallow incline, that's any angle less than 45 degrees, then you can see the development of the F parallel and the F perpendicular forces. The F perpendicular will always be equal and opposite to the normal. This new F parallel is the accelerating force, which draws the object down the ramp. A perfect incline is theta equals 45 degrees. The green and blue component vectors of the weight are now perfectly equal to each other because the sine of 45 and the cosine of 45 are the same. A steep incline is any angle over 45 degrees. And here we can see that when I tilt this ramp much higher than 45 degrees, I also change the lengths or magnitudes of the parallel and the perpendicular components. It turns out that the steeper I get, the longer the parallel component is, and the shorter the perpendicular component is. And you can see that the object will accelerate more quickly towards the bottom of the ramp because more of the weight component is acting on the object than it was down at a shallow angle. And you could also see that there is a foreshortening of the perpendicular component and its reaction force, the normal. And now the vertical incline is a 90-degree angle. This literally is free fall. An object which is inclined at 90 degrees only has this weight vector which happens to be the same as the parallel component. The parallel component, as you can see, is parallel to the surface, which is now a type of vertical wall, and it just pulls the object straight down. There is no ability of the surface to hold up the object because the normal force, as you can see in these pictures, is tilting from a pure vertical vector to a sideways vector while foreshortening. As you get to the vertical position, it is foreshortened to a 0 magnitude, which means that it disappears. There is no ability for the surface, now a wall, to push out against the block. The only thing acting on the block is pure gravity. Mass times gravity is the weight of the block, which happens to be the full parallel vector, parallel to the surface. In this chart below, you can see the magnitudes of the parallel and perpendicular components mathematically worked out for you based on particular angles. So I've chosen 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. When I plug in the values of angles for 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees, into each one of these expressions, the sine and cosine values are the same as a standard trigonometric table. Let's take a look briefly at the magnitudes of each of the forces mathematically based on these angles. When it is a 0 degree flat angle, you can see sine of 0 equals 0, cosine of 0 equals 1, and you have a full vertical component and a 0 horizontal component. When the angle is 90, you have the complete opposite. Sine of 90 equals 1, cosine of 90 equals 0, and you have a full parallel component and a 0 perpendicular component. When you have a 45 degree angle, you have equal components. The sine of 45 is 0.707, and you see that the blue and green vectors are equal to each other. For 30 degrees and 60 degrees, these complements, they actually have values of 0.5 and 0.87 respectively, except when you have a low angle, the parallel vector is sine of 30, which gives you 0.5, and when it is a 60 degree angle, you have the sine of 60, which gives you 0.87. So the values swap, just like they would in a regular trig table. So what we've done here today is take a look at all of the force components on the inclined plane that are produced by having an object on an angle so that it can slide down the ramp due to the effect of the weight vector. I hope you enjoyed this video, and I thank you for watching. In the next video, we're going to do an inclined plane problem using all of this mathematics to determine various factors related to an object accelerating down an incline. See you in the next video.